Bismillahirrahmanirrahim. So last time we discussed the concept of MACs, and hopefully after the lab they make a lot more sense, and you understand how the packets are taken from one location to another location within a local area network, right? So hopefully that was the purpose of the thing, and we started a little bit with the logical addresses, and we kind of used them in the lab as well, even though the logical address was not used too much in the lab, but it was there, right? So basically what we want to do now is look at the same scenario with a little bit of detail. So we have two topics to cover basically today. We have basically two topics to cover today. One is to finish off this topic of how packets go around in a network. Okay, so we have already seen what happens if you have one or two or three or four switches, but it's the whole same network. Okay, you'll understand exactly what I mean by the same network in a while, right? But it was just one collection of things, very small, and there were just switches in the middle, and you were able to communicate, right? So even if you had three switches, you could get to the PC after the third switch. Okay, so we've done that. So we have to finish off this topic. What happens when you have different networks? Right? So what happens then? We have to take a look at that, and then we are going to start off with our first layer. So essentially throughout the course, what we're going to do is we are going to look at all the 7 layers. Okay, so we are going to start with the first layer. There is very little in the first layer. I'll do the introduction when we get to that, but let's first finish off this topic. Okay, so we've already seen that we have what is called a logical address. So you can have an IP address. Okay, so when we started doing the ping, we had one source address and one destination address, right? So source IP address and destination IP address, we had that thing. Okay, for example, over here PC1 has the source destination address of 192.168.1.1.110, right? So last time in the lab we did 192.168.0.1 and 192.168.0.101, and we were able to do the ping, right? But if you remember, I told you at that time that you have to have 192.168.0 exactly the same. If you change it, then it's not going to work. Okay, so this is important. This thing, the portion that you cannot change, right? This is important, right? So we'll get to this. But see over here, at least you can understand that even from the very first part, it's not 192, it's 172. So it's different. Okay. So what this means, and again, we'll get to this, why it is different when we get to the third layer. But for now, all you have to understand is that they're not on the same network. Why? Because the first part is different, right? Again, why is that? It's a whole chapter, right? So we'll see all the details of why, what makes a different network, what makes the same network, because they're all connected using wires. So we can say they are the same network, but from the network's perspective, from layer 3 terminology, they are different networks because their numbers in the beginning are different. Okay, again, it's going to make much more sense later on. This device over here is a router. Because of the difference between the British pronunciation and the English pronunciation, some people call them routers, some people call them routers. Some people call this path route, some people call them route. Okay, and some people call the path route and call the device router. And some people call the path route and the device router. So it's any combination. Okay, so but you can use which. I use both, depending on, I don't know what depending on, but I use both. Okay, so it's the CISCO people, because they come from US, they call them the routers. So this thing is called a router. For now, all you have to understand is that a router essentially separates two networks. So if you have 5 pieces here and 5 pieces here, and there is a router in the middle, that is going to mean these are different. These are on a different network and these are on a different network. Again, why is going to be later on. Okay, for now, just understand that router essentially is going to act like a boundary between two networks. Okay, router, not switch. Remember last time we added switches. Okay, so the basic switch, the definition of switch, the thing which is called a switch, does not separate networks. Okay, another way to understand this is, which is going to make more sense to you, that if you send a broadcast packet, all the places that it reaches are one network. Okay, but that's not going to make much more sense, because at the moment the definition of broadcast that we have is it reaches everybody. Okay, but it's going to make more sense later on, right? So do you understand that you may have different networks even though they are all physically connected, but they can be logically two different networks because we have a router in the middle. Is this clear? Okay, so what we are discussing today is what happens. in your IP address, you have two parts, right? So an IP address contains two parts. So 192.168.0.1, it has two parts. This is the first part, the first three. This is called the network portion. Okay, and this thing over here is called the host portion. Okay, so it doesn't have to be 3 and 1. Okay, again, there are a lot of rules related to this, which we'll do in a separate chapter. There is going to be a complete chapter defining what the network portion is, what the host portion is. But for now, this thing, the first three parts are our network portion. The way it's defined is the first few bits are the network portion, and the final few bits, the remaining bits, are the host portion. Okay, that's how it's technically defined. For now, just look at the first three portions, right? So the first 24 bits are going to be the network, and the last 8 bits are going to be the host. Okay, so what this means is, if you have another IP address which has the same 192.168.0. same network portion, if two IP addresses are given to you, this is important to understand. If two IP addresses are given to you and I tell you how many bits are for the network, I'm telling you the first three portions, 24 bits are for the network. Okay, so if they are the same, then these two IP addresses are on the same network. Kind of makes sense, right? If the network bits are the same, they are on the same network. The host bit will be different because that has to be unique. I'll say this again. Depends on how many bits are given to the network, how many bits are given to the host. Yes. Again, the rules will be later on. For now, the rule is, if I tell you two IP addresses, if I give you two IP addresses, and I tell you how many bits of this IP address are for the network definition. Okay, so I tell you over here 24 bits, the first 24 bits are for the network portion. Okay, so that comes to these three blocks, 8 and 8 and 8. 8 3s are 24. Okay, this clear? So if I tell you that and I ask you, given these two IP addresses, are they on the same network? What do? You look at the network portion of one IP address and the network portion of the other IP address. If they are the same, then they are on the same network. Okay, is this clear? Perfectly clear to everybody. This is going to be important for us. Okay, so again, these rules, it's a complete layer. It's probably the most important layer in our course. So we're going to spend a lot of time on these rules. But you have to understand this basic principle for the sake of our discussion here. This clear? So let me give you an example. So I have 192.168.0.1 and 192.168.1.2. Okay? And I tell you that the first three portions over here are for the network. Are they on the same network? These two IP addresses, are they on the same network? No. Why? Because the network portion is not the same. Okay? Clear to everybody? Okay. Exactly same IP addresses, but now I tell you that the network portion is the first 16 bits. Now, are they on the same network?
Yes.
Yes. Is this clear to everybody? Okay, good. I made a horrible mistake over here, but that's okay. Okay. You don't have to understand the mistake right now. You'll understand it later on. Okay. Is this okay? So if you understand both the questions that we had right now, you're done. Okay. So now the question which we actually want to target is, what happens if you want to send a piece of information from one PC which is on one network to another PC which is on a different network? Yes. So the other one is on a different network. We have to see how the routing changes. Okay. So we saw that we had the source destination and the source IP address and the destination IP address in our packet. Okay. We saw that in the lab. We also saw that we have the source MAC address and the destination MAC address in the packet. Everybody remember that? Okay, good. So now what happens is, your MAC addressing, please, your MAC addressing can only work on the same network. You cannot know the MAC addresses of the other network. This is by design. Let's try to figure out why that is first. Okay. So remember that I told you that when you are studying networks, you have to think about not a very small network. You have to always keep in mind that when things are going to connect to each other, it's going to lead to the global scale. Okay. So the whole world. So if you are going to communicate with the whole world and you are going to send out a broadcast, and a broadcast by definition goes to everybody. If it goes to everybody, then every broadcast from every system is going to go to everybody in the whole world. Can you imagine how horrible that would be? Like every device in the world, the billions of devices, every device connecting to every other device. That would be like a bad idea, right? For example, if I plug in a new device over here and try to communicate with anybody, remember the first time we send out a broadcast packet, right? So I'm going to be sending out a broadcast packet to the whole world, which would be bad because it's not just me. Then anybody who wakes up in the morning and turns on their mobile phone or their PC is going to be sending out broadcast packets to everybody. Everybody understand? So we don't want to send out broadcast packets. We want to limit the broadcast as much as possible. Everybody clear on this? Right? So if you have 5 devices connecting to 5 devices, you're going to have 5 square connections. If you have 100 devices and 100 devices, you are going to have 10,000 connections. Everybody see how quickly this, so you have, if you have 1,000,000 devices and 1,000,000 devices communicating with each other, then it's going to be 1,000,000 into 1,000,000 is, I don't know, like a zillion or something. It's more than a trillion. It's like a horrible scenario. Everybody understand? So we cannot have broadcasts. So what IP address does is it gets rid of the broadcast. We'll see how later on, but for now, let's see how the scenario works. Okay, is this clear to everybody? So for IP version 6, for now, forget about this. When we have a separate chapter on IP version 6, then we'll discuss this. If you understand the network portion is for IP version 4, it's fine, right? So the IP that you see over here, 32-bit IP address, that is IP version 4. There is a newer version which we'll get to later on. For now, IP version 4 is fine. Is this clear to everybody? Okay. So what does the network layer, network layer does? Okay. So network layer addresses, what are the points? So remember over here, so we have the MAC address over here and the MAC address over here, the source and the destination, right? So this person is trying to send a piece of information to this thing. They are on the same network. Okay. How are they on the same network? 192.168.1.110, 192.168.1.1. Are they on the same network? The network portion, you need to ask me how many bits are for the network portion. 24 bits for the network portion. Now tell me, are they on the same network?
Yes.
Yes. Is this clear to everybody? If I give you 2 IP addresses and I ask you, are they on the same network? You have to ask me how many bits are for the network. Okay? Without that, it doesn't work. Because the same thing, I can say all of these are for network. All 32 bits. Then they're not on the same network. Understand? Okay? Doesn't work like that, but kind of. Okay? Is this clear? Alright. So let's get rid of this. So if you want to communicate from PC1 to R1, which is router 1, it's the same thing. They're on the same network. It does exactly the same thing that we did in the last lab. Is this clear? You first send out a broadcast packet. If you say ping from PC1, if you say ping 192.168.1.1, a broadcast packet goes out, blah, 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 and you get the MAC address back. And then you send the communication to this, as we did in the last lab. Okay. But what happens if you want to send a piece of information to R2? Is R2 on the same network? You have to first ask me how many bits are, but I assume you're taking the same thing. Yes, 24 bits for the network, yes. Right, so 24 bits for the network, so it's on a different network. So now the routing is going to be slightly different, okay? So again, the details are going to be later on, but for now, we just want to finish this discussion. So what's going to happen is, you are going to have first the data link layer addresses. So these are the MAC addresses, okay, on layer 2. You saw they were on the layer 2. If you don't remember, I'll remind you that layer 1 is the Ethernet layer, which is the physical layer, and layer 2 is the MAC address layer. Okay, so you had the MAC addresses written on your layer 2, and you were trying to send that piece of information over here. So these were MAC addresses. So MAC addresses, what happens when you try to access an IP address which is on a different network? Then MAC addresses are not sufficient. So here's the rule. You are going to have what is called a default gateway. Okay, if you remember, we did this in the very first lab, but there we did not discuss how it works. I gave you a brief definition. Here I'll give you a slightly more definition, and then later on in the chapter we're going to have a lot more details on this. So here's the slightly more technical definition of a gateway. You are on a network. Now you know what that means. The network portion of all the devices on this little portion of the communication area is the same. Network portion of all the IP addresses is the same. This is what is called a local area network. Okay, same network, local area network, different ways of saying the same thing. Okay, if you want to communicate with any device outside this network, you need a dedicated device. This device is called the gateway. If you want to communicate with anybody outside your network, you don't communicate with them directly, you go talk to the gateway. And it's the responsibility of the gateway to take your information and send it outside the network, wherever that outside is. So again, if you want to communicate on the local network, we did that in the last lab. Done. Okay, that is all there was, nothing further. Okay, is this clear? Same network, MAC address, we did it last time. If you want to go to a different network, then you don't go to the end device directly, you talk to the gateway, which is going to be a specific device in each local area network. Okay, is this clear? A little bit, we're doing the details of this, but is it clear? There is going to be a specific device. I'm going to configure that device on my PC. I'm going to say, if I want to communicate outside my network, this is the person to talk to. Okay? Typically that's a router. Can be other things, but typically that's a router. And that is where router defines the boundary of a network. Good. That is why router defines the boundary of a network, because it's sitting there in the gate. That is why it's called a gateway. It's sitting on the gate, and that is where the network ends. If you want to go outside the network, talk to this person, this device. Is this okay? Okay, good. So this situation over here, this whole thing is our network. So I've put like half of the router inside my network, because router is going to have two interfaces. One which is on this network and one which is supposed to connect to some other network, which is the outside world. Understand? Right? Remember the first lab when we had the wireless router? We connected from PC to the wireless router, and then the wireless router connected to the internet, because that was providing us connectivity to the rest of the world. Is this clear? All of these pieces are interlinked. So you have to understand one piece to understand the other. That is why we are looking at each piece briefly and then coming back, and then looking at that piece and then coming back, right? So because slowly we're going to build on our knowledge. Is this clear? Okay. So now you have a router. So half of the router is in this network and half of the router is responsible for the rest of the world, as far as we are concerned. Is this clear? Okay. So we have a default gateway over here. All devices on the LAN must be told about the address on their traffic will be confined to LAN only. So all the devices on the LAN have to know who the gateway is. Okay, you have to tell this is the gateway. And how do you tell that? If you remember in our very first lab, when we did the DHCP, as soon as we clicked on DHCP, then the gateway address appeared, 192.168.0.1 automatically appeared. So DHCP can give you your IP address, and DHCP also tells you the gateway's IP address. When you say DHCP, remember DHCP a little bit? We didn't have to configure the IP, it was given to us first lab. Okay, I'll remind you. So first lab, the connectivity was not working. We clicked on DHCP and connectivity was established. We were able to access the internet. Why? Because the gateway was given to us by DHCP. And as soon as we found out what the gateway was, then we could do the communication. Is this clear? Okay. So again, we're going to come back to this, but for now, on all LAN devices must be told about the gateway address. Who's your gateway? If you don't know that, you cannot communicate outside the LAN. Okay. On layer 2, once layer 2 on PC1, so forget about this. We'll come back to this in the next few slides. Okay. So here's what happens. When you are trying to communicate with the different IP address, for example, if you are trying to send a piece of information from this PC, PC1, to the web server, which is on a completely different network, 172.16.1.99. Okay. So you are trying to go from 192.168.1.110, which is this guy over here, and you are trying to get to 172.16.1.99. Okay. Which, as you can see, is a completely different network. Okay. So the first thing, you have to know who your gateway is. Okay. So let's assume that the PC has already been told that the gateway is 192.168.1.1. And you notice over here that your gateway is always going to be on your same network, because you have to be able to communicate with your gateway. Otherwise, you will not be able to talk to the rest of the world. So if the gateway is outside your network, then it's not going to work. You understand? Because gateway is what you need to talk to people outside the world, outside your LAN. So if your gateway is outside your LAN, how are you going to talk to the gateway? So your gateway has to be on your network, same network, okay? Everybody agree? All right. So the general principle that you have to understand for the rest of the 3 slides is the general principle. Rest we are going to come back to the later on. If you figure out that you are trying to communicate with an IP address which is outside your network, you don't talk to that IP address. You talk to your gateway. Again, if I say ping on this PC1, if I open up the command prompt and I say ping 172.16.1.99, enter. As soon as I hit enter, the PC knows its own IP address. It has this IP address because I just typed it. It's going to look at both of them and decide, are they on the same network? If they're on the same network, it does the same thing that we did last time. If they're on a different network, the PC is not even going to try to figure out what the MAC address of this 172 something something is. It's not going to do that. It's going to send this packet directly to the gateway. You figure it out. Understand? We don't need this person's MAC address. We don't care. Why? Because we know we cannot communicate with it. So who are we going to communicate with? Our gateway. Is this clear? Okay. Once the packet gets to the gateway, then the gateway is going to look at it and decide, okay, where is this supposed to go? So let's say the router has 3 different wires connected to it. So one wire over here, one wire over here, one wire over here. So it's the responsibility of the router to figure out which path this packet should take further. We offloaded our task to the router. Everybody agree? We said, here's the packet. You take it. I don't care. Let's just get it to the 172 dot something something. Okay? We don't need the MAC address at all. The MAC address that we needed was our gateway's MAC address. But our gateway is on the same network as us, so we can get its MAC address using broadcast. I'll say this again. If I don't have the MAC address of my gateway, I can get it using the ARP protocol. Why? Because it's on the same network, and ARP protocol we already saw it works on the same network. Is this clear to everybody? Yes? Okay. So once you have the MAC address, you put in the source over here your own address, and in the destination you don't put the address of this device over here. You put the address of your router, which is 111111111 in this scenario. See? Who are we trying to communicate with? The source is, network is 192.168.1, the devices or host is 110. So our source IP address in this whole packet that we've created is our IP address 192.168.1.110. Okay? The destination is 172.16.1.99, the thing where we want to send the packet to eventually at the end. This is where the packet is supposed to go. Everybody agree? Okay? But in our Ethernet data link layer, the frame, which is the data link layer, there the destination MAC address is not that of 172.16 dot something something. It has a MAC address A, B, C, D, E, F, 1, 2, 3, 4, 5, 6, but we don't know that. Moreover, we don't need it. Why? Because I'm going to put the MAC address of my gateway. So the packet gets to my gateway. Okay? Do you remember how the ARP protocol allows you to send packets here and there based on the MAC address? Okay. If you have a switch, it can go to the switch forwards it to the correct MAC address depending on the information that it has in its address table and all of that. This is why these labs are extremely important, right? It's very, very important that you do them yourself. That is why I'm saying do these labs individually, because you need to do that in order to understand these concepts. If you don't do the labs yourself, the concepts are going to be like difficult to understand. Okay. So you have the destination MAC address of 1111111, which is our gateway, not 172, not the web server. Okay, is this clear? So now the switch is going to do its thing. The same way the packets, the frames go over here in the local network, they are eventually going to get to the R1. Okay, once it gets to the R1, so here's what's going to happen. From your original source to your R1, and then your R2, and then it's going to get to the final destination, right? So it's going to go over here in R1. Let's say there is a connection over here. So it's going to go from your device to the R1, and then it's going to go to R2, and then it's going to go through the switch to the web server, right? So we've simplified the diagram a little bit over here. Okay. for each of this big packet over here, the information that is relevant to us has two parts. One is the source and destination MAC addresses and the source and destination IP addresses. Is this clear? Yes, R1 and R2 are, so R1 is the gateway for this local area network, our local area network, and R2 is the gateway for that web server's local area network. Okay, and these two are connected to each other.
So there is two gateways.
Yes, but you never say two gateways because for one LAN there is only one gateway. That is also a gateway, but that is like another. For example, in any country, you would say there is only one ruler, one prime minister or one president, right? So you have one prime minister here and you have another prime minister there, but that is not my prime minister, that is like somebody else, okay? So there is always one prime minister. Because that, yes, but it's not my concern, okay? So one gateway always, okay? Right, so, okay, so here we have two portions, two things which we need to keep track of. Source and destination MAC addresses, source and destination IP addresses. So my source IP address is 192.168.1.110. My destination IP address is 172.16.1.99. They are going to remain the same. Okay, they're not going to change throughout our journey. But when we go from over here, so this L2, which is layer 2, which means this is MAC address. Remember, I told you that you have to remember the layer numbers because people just write them like this, layer 2. They won't even say which layer it is, right? So I'll remind you for a while and then you should like kind of have it memorized automatically. So layer 2 is the data link layer on which MAC addresses work. And layer 3 is the network layer is the internet layer on which the IP addresses work. Okay. So this thing is the IP address portion. So this is the IP address and that is the MAC address. Okay. Is this clear? Okay. So let me just go show this to you just in case you have forgotten. Right. So layer 3 is the network layer. Okay. Or it's also called the internet layer. Okay. So over here. So now see over here, when you are sending your information to your router, you are going to have the destination. This guy is going to be your destination. Okay. So here you are going to have in the source PC1 and in the destination R1. Okay. For the MAC addresses, this thing over here. Okay. For IP addresses, it's going to remain the same. Once the packet gets here, the router is going to open up the outer box. It's going to see the MAC address and it's going to decide, yes, this frame was indeed sent to me. So it's going to accept the packet. It's not going to reject it. Remember, when are packets rejected on your local area network? When the IP address is not your own. Okay. But here it has its own MAC address. So it's going to accept the packet. It's going to open it up and it's going to see that the destination IP address is somewhere here. Okay. So it knows where the different networks are. So it knows that it's going to send the packet over here. So it's going to now change the layer 2 information. See that the color has changed. It has gone from green to gray. Okay. What this means is in this layer 2, router 1 is going to change the information. It's going to say that the source is now me for the MAC addresses. Source MAC address is mine and the destination MAC address is R2, the next router. So it's going to offload it to that person. Okay. Router is a very special device. It knows a lot of information about the whole internet's network, right? So a lot of information. We'll have like, I guess 2 or 3 different labs just on the router. Okay. It's essentially what makes the internet work. Okay. So router is a very special device, very interesting as well when you actually can make it work. Okay. But the router knows that it has to send the information to R2 and R2 will manage to get it to the final destination. Okay. So here the MAC address is going to change. Source is R1 and the destination is R2. We have separate slides for this, but this is the overview. Then when it gets to the R2, R2 is going to know that yes, this 172 something something is on my network. So it's going to change this L2. It's going to say the source is now R2 and the destination is this final server. Okay, let's see them in specific slides and then it's going to make sense. Okay, so over here, it's going to have the L2 header is going to change. So over here in the very first portion, this is going to be, so what are the addresses? So PC1 is AAAAA. So source is AAAAA and destination is 11111. Okay, the first time. When it gets to router 1 is going to open the outer box. It's going to throw away the source and destination MAC addresses and assign a new frame, like new information in the frame address are going to be changed. It's going to put over here, it's going to put its own, so 111111 is going to be the source, and the destination is going to be 22222, which is R2. Okay, and now the packet goes out again. When it gets the R2 using the same R protocol, when it gets to R2, the R2 is going to again look at this, it's going to put its own MAC address as the source, and the destination address is going to be, yes, what is that? A, B, C, D, E, F, something, something. Okay, so A, B, C, D, E, F, something, something. But notice that the IP address in all the portions, source IP address and destination IP address, always remains the same. So we say, then when you are trying to communicate on a different network, your MAC addresses are going to change on each hop. This is called a hop. You know what a hop is in English? The thing that a rabbit or a frog does? The jump, the little jump. That is called a hop. Right? So the difference between a jump and a hop is, I think that in a hop, you're just sitting there and you jump. And in a jump, you have to run and then jump. I don't know, I'm just making this up. Okay? But a hop is like a little jump. So this one thing is called a hop. From R1 to R2 is a hop. Okay? So the MAC addresses changes, the source and MAC address pair changes on each hop. But the source IP and the destination IP remain the same. Okay? So once this packet gets to the very final portion over here, the final web server is going to look at the destination IP address. That is going to be its destination IP address. Everybody agree? It has the IP address of 172.168.1.19. The packet that it sees has its own IP address. Remember, you look at the IP address. If it's your IP address, then you accept the packet. Okay? And the MAC address, the destination MAC address, is also its destination MAC address. Right? Because that is what was put there by R2. Not by PC1. PC1 doesn't know. PC1 sent the thing to R1. R1 sent the thing to R2, and R2 put the destination address of this. How does R2 know the destination of address of this final server? Because R2, half of R2 is on the same network as this guy. Okay, so this thing over here is the same network. So that is why this R2 knows the MAC address of this guy, because of the R protocol. So you see, now you have very small pieces coming together, and now you can connect essentially an infinite number of different devices very efficiently. Okay. Now if a broadcast happens, the broadcast is going to be limited to this portion over here. The broadcast does not go to the whole world, but we have still managed to communicate with the rest of the world without doing a broadcast. Yes.
You said PC1 sent the message to PC2 and PC2 sent the message to PC3. Then PC3 sent the message again.
Yes. So I'll fix the terminology. I'll fix your terminology, and then you can ask the rest of the question. Maybe I said it wrong, but I'll say it again correctly this time. So PC1 sends the message or the frame to its gateway, which is R1. Let's call it R1 so that we know it's a router. Because I told you router is a special device.
Yes, okay. So to the router.
Then R2.
Then R2, then R3. Then R3 sent back to R1. How?
Not back to R1, to the server. Right. So let me draw this cleanly, right? So PC1, right? It's okay. I said it's possible. So she's not completely wrong. We're actually going to do a scenario like this later on, like after the midterm or near the final. So it's a good use case, but that is not what we're looking at over here. So PC1 sends to R1, R1 sends to R2, and R2 sends to the server. This is the scenario we have right now. Okay, so it's fine now? Okay, we have that scenario, but later on in the course. Okay, we are going to have that. So that's a good question, but like way ahead of its time. So just wait on that. So is this clear now? Okay, good. All right. So that is it. So that is all we're doing right now. So if you understand that your MAC addresses are used for communication on your local area network, they're also used for communication outside your network, but not your MAC addresses. So when you're sending from R1 to R2, you do have MAC addresses, but we don't care about them because they're outside our network. As far as we are concerned, all I had to know was the destination IP address and the MAC address of my gateway. Okay, that's all I need you to know. And that you will kind of agree that that is very little configuration to do. We don't have to worry about the rest of the world at all. Is this clear? Okay. So this is the end of the chapter over here. It should leave you with a lot of questions. Like, I'll give you a few questions. For example, how does R1 know that it's supposed to send the information to like R2 and not R3? There are two wires going out, right? So how did it know that it should send the information over here and not over here? Okay. Also, how are these MAC addresses, how are they being translated, how are the frames changed, and all of this information. So this is going to be later on in the course, right? So how many types, what is the size of the network portion, what happens if you reduce the size, what happens if you increase the size. There are a lot of questions. We're going to come back to this when we get to layer 3. Okay, is this clear? Okay, but we are first going to start with layer 1. So we have the layers starting now. So we are starting with the very first layer. It's the physical layer. It's probably the most boring layer there is. So we are just going to like run through it really quickly. It doesn't have any information that is really going to concern us later on. It just has some terminology that you should know. If you've taken a network course, you should know this terminology, right? So we're just going to go through this. There is nothing technical here, nothing that you need to like memorize, but I mean, you should know the terminology, okay? So physical layer, what is the physical layer? Physical layer is the prerequisite for establishing a network. In the real world, you need to have something for two devices to communicate with each other. It doesn't have to be like a physical solid. It doesn't have to be a wire. It can be wireless, but there has to be something there which can connect two devices together. Okay. So that is the whole purpose of the physical layer. The first thing which is going to be the most important for the physical layer is going to be your network interface card, which is NIC. So the network interface card or the NIC, NIC, that is essentially the first bit of the physical layer. Okay. That falls in the physical layer. And that is what I mean by we don't really concern ourselves with the physical layer. You get a network card, you plug it in, you're done. Okay? We as network administrator, IT people or CS people, we don't really concern ourselves with the network card. There are domains out there, and those are very lucrative domains, but there are domains out there in which people decide on how much power the network interface card uses, how much power can you give it, what kind of device you need to have it. There is a complete domain of server design in which people talk about how large of a rack you need if you have a data center, how many racks you're going to need, how are you going to cool the thing, because machines generate heat. So if you have 5,000 machines in a room which is this big, it's going to heat up a lot. So you need to cool it. So there is a complete domain. I'm not saying it's not useful. I'm saying it's not our concern. Okay. By the way, there is a website called serverfault.com. Very interesting if somebody is interested. So SERVER, serverfault.com. This is a sister website to Stack Overflow, and it has really weird people on it. So which is to say that they talk about really strange things. They talk about how to like color code your cables and how you can make them look nice, and it's a good area if you're interested in this. But anyway, we are not interested too much in physical connections. So the physical layer, essentially, we've already seen that it works on this portion over here. Okay, so Ethernet, MAC addresses, all of this. So remember, your physical layer, which is layer 1, in the OSI model, is equivalent to like the half of the network access layer in the TCP model. Right? So if you don't remember, I'll remind you, TCP model has 4 layers. The first 2 layers of OSI map to one layer of the TCP IP. Okay, so where is it? So the first 2 layers map to the network. So anything that we talk about in the physical layer, if somebody asks you where is the network interface card in the TCP IP model, you're going to say it's in the network access layer. Okay, for my particular course, you don't have to memorize this. Okay, but it's very useful in the real world, because if people are talking about, for example, the network access layer, and you are just looking at this, you might mistake it for the network layer, right? So network access layer of TCP IP and network layer of OSI model are completely different. They have nothing in common. Do you understand my point? So you don't have to memorize them, but you have to know them sufficiently that you don't make mistakes like this. Okay, if somebody says this is on the network layer and you mistake them to mean network access layer, then it's going to be completely different. Is this clear? Okay. All right. So we are over here, we've already done this. So physical layer has like 3 functional areas: the physical components, how do you encode stuff, and how you send out the signal. All 3 of these are not really our concern, but we're going to go through them for the sake of completeness. So encoding is essentially at the physical layer. Encoding means this thing: you take the bits and you somehow convert them into voltages. Okay, so high voltage is 1, low voltage is 0, or let's say in the fiber optic you have the light pulse. When the pulse is sent out, that's a 1. When the pulse is not sent out, that's a 0, something like that. Okay, not our concern at the moment. Essentially, you can imagine that it's going to somehow convert the bits into some sort of a physical medium. Okay, all right. So you have 2 important concepts over here. So one is bandwidth. So bandwidth is the capacity at which a medium can carry data. So how many bits per second can you carry? That is called the bits per second. This is the bandwidth. If the number of bits increases to a very large number, you change them to kilobits per second, which is 1000 bits per second, or 1024, okay, or a million, or a billion, or something like that, right? So you already know these things, right? So kilo, mega, giga, tera, and you also have peta and all of that stuff. Okay, 2 very important concepts. One is latency, and the other is throughput. Both of these are somehow related to the speed. So you have to understand the difference between these 2. They come up again and again in computer science. So latency means if you start from point A and you get to point B, how long it takes you. So it's a measure of time. Okay, so this is latency. Everybody understand? If you start from point A and you get to point B, how long it takes you? What is the delay? That delay is called latency, right? So the technical terminology is latency. So latency is the measure of time. Okay, is this clear? Okay, so if you measure latency, you're going to say seconds or milliseconds or microseconds or hours or something like that. Latency is going to be measured in time. Throughput is the number of bits. So for example, you are looking at one portion over here, B, and you say how many bits are coming in per second. How many bits are coming in per second? So if you are looking at this, you don't care when the bits started. They could have all started 15,000 seconds ago. But here, if I look at just a 1 second window, how many bits fall through? So think of this way. You're looking at a pipe, right? And you are looking at how much water is coming out. Is a little bit of water coming out or a lot of water coming out? That is called throughput. Okay, so throughput is for one particular point in space, one device. Okay, throughput. And in order to calculate latency, you need to have 2 things, because you need to say how much time it takes to go from here to here. It has to have from here to here. For throughput, you are just looking at one thing and you are seeing how many bits are going through this one thing at a time. Okay, both somehow measure speed, but it's going to have different effects. Okay, it's possible to have a very large latency with very little throughput, or very large throughput with very little latency. Okay, you just have to kind of know the concepts. Later on, we're going to come back to this when we need them. Is this clear? Okay, so let me say this again. Latency is the speed with which this thing gets from here to there. So you measure it in seconds or time units. How long it takes for a bit to get from here to here. And throughput is you're looking at one point and you're looking at how many bits are passing through this one thing at one particular time. In 1 second, how many bits pass through it? Is this clear? Okay. All right. So then in the physical layer, this is all like disconnected concepts, but we have different types of connectivity. So you have cables, you have fiber optic, and you have wireless. Basic 3 things. Okay. So cables, there are basically 3 types. There are 2 concepts which are important for cables, which are attenuation. So attenuation is if you have a wire and you send out a signal, it's electricity. So after a little while, it's going to get weaker. The signal is going to get weaker. It's electricity. There is a certain point until which your electricity is going to have some effect, and then it's not going to have any effect. So the signal is going to have like interference, and it's going to get lost after a little while. So attenuation is the distance after which your signal is no longer useful, kind of, right? The longer the electrical signals have to travel, the weaker they get. So this concept of getting weaker after a little while is called attenuation. So signal is very strong, clear 1 and clear 0 initially. And then after a little while, because of interference from physical world and environment and everything, the 1s and 0s are going to get very close together. So it's going to look like 1, 0 and 1 and 0. And after a while, it's going to be like, So this is the concept of attenuation. Why is this happening? Because of physical factors. Okay, maybe the wire is old, maybe there is rain, maybe there is water, maybe there is some other stuff going on. Okay, is this clear? The other is interference. So interference essentially means that when you have electricity flowing through a wire and you have like magnets around it, they can affect the electricity, and there are many magnets, and if there are other wires, they can also affect this, and it's a big mess. Okay, so this is just interference. Again, not really that big of our concern, but you have to know the terminology. Okay, so all the blue stuff you have to know. Okay, is this clear? Kind of. I mean, nothing technical. It's not difficult. It's technology. Okay, so there are three types of cable that you have to know. One is called the unshielded twisted pair. So as the name suggests, it's going to have pairs of cables. They are going to be twisted with each other, as you can see, twisted. Each pair has two things, one light and one dark. So these are pronounced as orange light, orange dark, green light, green dark, blue light, blue dark, brown light, brown dark. So this thing over here, this is a light. So it's not actually a light color. It has white and orange both on it. So it looks lighter. Okay. So I'll probably bring some cables and show them to you, but you can look them up online as well. So orange light, orange dark, green dark, blue dark, brown light, brown dark. Okay. So each pair is twisted, and they are not shielded. So there is no shield around it to protect it from interference. This is called the unshielded twisted pair cable. Is this clear? Okay. It has four pairs. Each pair has two cables, one light and one dark. Orange, green, blue, brown. Okay. I'm not going to ask you to remember them, but you're actually supposed to remember them. For this course, I'm not going to ask you to remember them. But we remembered these back in, I guess, 2002 or 2003. And when I was preparing the lesson, I could actually recall it after all these years, because we made these cables and it's going to mess up if you don't remember the encoding, right? So I'll tell you what I mean in just a minute. If you put a shield around the cables, right, all the pairs, if you put shields around them, which is to say some sort of like mesh, which reduces interference, it becomes shielded twisted pair cable. Okay, STP cable. So these are the most common cables. So the cables that you see over here, they are shielded, the things which go into the PC, they are shielded twisted pair cables. Okay, so these are the most common cables. Okay, all right. And this thing over here is called the RJ45 connector. So it's the name, RJ45. So this RJ45 connector is the standard. So you have all the 8 pairs. So you can probably see the 8 pairs going in over there. So they go into their own slots, and then you basically staple them inside the connector, and then the connector goes into your NIC, network interface card. Okay. So this is called the RJ45 connector. Okay. So if you talk to any IT person, they're going to ask you to check your cable, and if you don't know what cable, they're going to say your RJ45 connector. Okay. So you have to know the name. Right. So these are only the things. There were quite a few slides in this chapter. I deleted all of them because they are not concerned or are concerned. So the stuff which is left is useful. You actually come across this terminology. Okay. So this is the RJ45 connector, and this thing is the RJ45 port. Right. So you plug it in. You plug the connector into the port. Okay. And you can probably see. Look at a PC and you can like see that it's connected over there. Okay. So this is the RJ5 connector which goes into the RJ45 port. This thing is the coaxial cable. So as the name suggests, it has an axis, and both wires have the same axis. So coaxial. So co means sharing something, right? So coaxial essentially means one wire is in the middle, this thing over here, and the other wire is kind of a mesh around it, but they share the same axis, right? So they're called coaxial cable. You don't have to understand why the name is, but it helps. So this is called the coaxial cable. This is slightly higher bandwidth. Sometimes you use this to connect to other thing, but this is going out of fashion very quickly, right? But this you actually connected your cable modem, cable modem to the internet using the coaxial cable, right? It's okay, I don't remember either, but you have this. All right. So when you have the shielded twisted pair cable or unshielded twisted pair cables, you have 8 cables in there, right? 4 pairs, each with 2 cables. So total 8 cables, right? And they go in a particular order. Okay. So the order is, you have green light, green dark, orange light, blue dark, blue light, orange dark, brown light, brown dark. This looks very weird. So let's look at the proper order first. So this is pair 1, orange light, orange dark. then you have green light, blue dark, then you have blue light, green dark, and then you have brown light, brown dark. Okay, so the reason for this is, so you have these two standards. Okay, one is called T568A. You don't have to remember the number. Okay, it's fine. You just have to remember that there are two standards. Okay, both of these standards are going to go on the other ends of two. So you have a wire, so forget about this. You have a wire, you have 8 wires coming out of this single wire here and 8 coming out here. Everybody clear on this? Okay. So if you put them in a particular order and you use the same order on the other end as well. So if you go orange light, green light, blue dark, blue light, green dark, brown light, brown dark, and over there you go orange light, green light, blue dark, green dark, brown light, brown dark. Same combination on both. This is called a straight cable. Everybody understand? Same combination on both ends, it's called a straight cable. Okay, so a straight cable, this is called a straight through cable or just a straight cable. It has the same combo on both sides, or let's say both ends of the cable. Okay, you're going to have an RJ45 connector here and an RJ45 connector over here. If they follow the same sequence, then they are straight through. And you remember you connected straight through cable from your PC to your modem or wherever. Okay, if you change the combination from one to the other, so if you pick one of these for one end and the other of these for the other end, you can see they are both different, right? So if you have on one end this standard and on the other end this standard, then this becomes a crossover cable. Okay, there are historical reasons for this. You might be thinking, why are we doing this? There are historical reasons for this, for increasing efficiency. Nowadays it's not that important. So as you will see over here in the slide, it's going to say if you are trying to connect host to host or switch to switch or router to router. You remember we did connect a switch to switch, right? In our previous lab, we connected a switch to another switch and we connected it using a straight cable and it worked, right? These are slides from CISCO, not from somebody else. So it's still recommended that you use a crossover cable for, there is a crossover cable in the list in the packet tracer. Right next to straight cable, there is a packet tracer, there is a crossover cable as well. You can select that. So the point is, if you are trying to connect two different types of devices, so for example, switch to a PC, okay, or PC to router, different devices, you use a straight cable. If you have same devices, so switch to switch, router to router, you use a crossover cable. Okay, this is historically and this is good practice. But nowadays, even if you have straight cables for everything, it's going to still work. I think somebody noticed, I don't know, somebody in this lab or some other lab, but somebody noticed that in the lab screenshot that I shared, the wire was dashed. So that was a crossover cable. So when I was preparing it myself, I had the thing right. But when I was recording the video, I messed up and I just put the straight cable. But straight cable also works these days. Okay, there was a time when if you wanted to connect a switch to another switch and you had only a straight cable, you could not do it. You had to like cut it and then change the combination, then the switch would work. Okay, but nowadays even straight cables work. Okay, but it's still generally good practice to have crossover cables, but because you're not going to be creating like doing many cabling things, so it's not all that important. So is this clear? Okay, so I'll summarize this thing. There are two possibilities of creating connection ends. If both are exactly the same, then this is called a straight cable. If one is following one standard and the other another standard, so if you're going to change, then you have to follow the standard. You cannot like think of another combination and use that. It has to be this because the software is going to need it. Okay, so if you have one standard on one end and the other standard on another end, then this is called a crossover cable. Essentially because the pairs are going like this and then they are being switched in the middle, right? So it's not important. Okay, there is also what is called a rollover cable. So this rollover cable is Cisco proprietary, and this is used to connect your router or switches, Cisco routers or Cisco switches to your PCs. Okay, so this is not that important for us. We're going to see these cables later on, inshallah, in some session. Okay, is this clear? All right. So fiber optic. In fiber optic, you have they work over longer distances. They work on the concept of lights. So you have a very fine glass pipe. Everybody has seen a gas pipe, right? Have you seen a gas pipe? the thing that goes into the cylinder and then into the stove, right? So the gas pipe, right? So it's kind of like that, but it's very fine. It's like 1 millimeter or even smaller than that, and you essentially send light in it. Okay, so that is what a fiber optic is. All of you probably have fiber optic in your home, but you've probably never seen it. But you have fiber optic. They are good for longer distances because light has very little attenuation. Do you understand what that means? Attenuation is signal getting weaker over long distances. Okay, so attenuation. The longer the signal has to travel, the weaker it gets. Light has lower attenuation, which means it can go for a long time before it gets messed up. Okay, so that is why fiber optics are used. They are completely immune to interference because it's light. Electrical pulses do not affect it. Okay, blah, blah, blah. They are used for. Do I have something over here? Right. So they are used for enterprise networks because they are expensive. They are high speed. They are used for fiber to home. So all of you, the connection that you have at home, the 20 megabits and 100 megabits and I don't know 200 megabits, all of that comes to your home. The cable that is coming inside your home, that is a fiber cable, and then from that little device, it goes to a router. That is a straight through cable. I think that is a different. Anyway, so you get today's high speed internets at home are almost all fiber based. Okay. You also have long haul networks, so larger between countries and cities, and you also have submarine cable networks, right? So there is, I don't have a screenshot, but you can search for it. The submarine cable network of the internet. If you search for it online, you will see that around the whole globe, all the countries in the world together have come together and they have installed huge fiber optic cables which go under the ocean, like literally under the ocean. They go alongside the beaches under the ocean and they are spread across the whole world. It's a very nice image to look at. I'll show you this to you, but you can search on it yourself as well. Okay, so those are also based on fiber, because if you are going to go from one continent to another continent, you cannot do copper. Electricity is simply not going to work because you cannot install a pole in the middle of the ocean to like reinforce the electricity. Okay, anyway, so for your fiber optic, you have different types of connectors. So these are called straight tip connectors, lucent connectors. So this one you've probably seen somewhere in your home. So it goes into the device, and this is like other connectors. We don't have to concern ourselves with this. Okay. Okay. Finally, wireless media. So in wireless media, you get a large coverage area, because a wire, if you want to take from here to there, it's going to be a mess. But wireless can work. Okay, it has a lot of interference because it's going over the air, and there are other stuff as well. And because it's not protected by a physical medium, it also has security concerns. Okay, whenever people start learning hacking, almost the first thing that they do is that they hack a wireless router, an unprotected wireless router. Anyway, for wireless media there are standards. The most important one is the Wi-Fi standard. So the number for this is 802.11. So IEEE creates different standards and they give numbers to each of them. You don't have to remember the numbers, but you just have to know that it looks something like this. So 802.11, then you have variations A, B, G, and different variations in the past few years. You also have Bluetooth, which almost all of you use. You also have WiMAX. So at a point, WiMAX was very popular, but I don't hear about it anymore. You also have Zigbee, which if you go into Internet of Things, you're going to come across this standard a lot. Okay, so the Internet, have you heard of Internet of Things? Internet of Things. Go look it up. As a computer science graduate, you should know what Internet of Things generally is. Okay, so in Internet of Things, you have devices connected to each other using the Zigbee protocol. So Zigbee again is something that comes up again and again. Okay. You also have wireless LAN, which is essentially the Wi-Fi that we use over here. So a LAN but connected through wireless. Same concept. From a software perspective, it's going to have the same concept. It's going to have a MAC address. It's going to have IP addresses. Same network, same IP address, same LAN, same concepts. Okay. And that is the end. So that is all we're doing with physical layer. There is obviously a lot of details to this. Like how do you make the connectors properly, which connector to use when, and which protocol to use when, the pros and cons and all of that. But that's not our concern in this course, right? Because we don't concern ourselves with the physical stuff. We want to get to the software layers and work with that a lot. Okay. Any questions? We are going to work with DHCP, and you have already worked with it before. Remember in the first lab when we created a PC network, a network on which we had a PC, and the PC could not communicate with the internet, we enabled DHCP, which essentially gave us an IP address, and then we were able to communicate with the internet. Okay, so in this lab we are going to look at this in detail. There are different reasons for this. The primary reason that we're doing this lab right now is that we want to work a little bit more with the IP addresses and like get to know them before we get to further protocols. The other thing is that DHCP is a very simple protocol, and you're going to see through this example what a protocol actually looks like and what are the essentially the aspects of a protocol that you have to understand in order to learn any protocol. So we're taking this as a case study, and what we're going to do is we are going to create a very small network over here, and we are going to have a PC which is going to be configured using DHCP. So let me tell you what that means. So we are going to go over here in our end devices and we are going to place a PC over here. Okay, so if you click on the PC and you will see this thing over here, you go to config and you will see that at the moment the gateway is set to static. So we've already seen what a gateway is. The gateway is set to static, which means I have to define what my gateway is right now over here. So I have to define it. Okay, I don't know what my gateway is. Think of it this way. If a user comes into your network, you want to facilitate them. They should need to do as minimal of a configuration as possible. Ideally, what you want is a user comes in and they connect to your network either through a wire or wireless, and they should be done. They shouldn't have to worry about what an IP address is, what a gateway is. All these configurations should be done automatically by our network for them. Okay, so here's the idea. This is a user who has come in, they want to join our network, and they shouldn't have to do any IP configuration. So the user should not have to do anything, and it should be automatically done for them by our network. Okay, so that is the idea. So let's go ahead and close this and create our network around this. So we are going to have a switch over here. So let's create a switch. It's not really necessary, but let's add it over here. Let's also go ahead and add another PC. So let's say this PC was already here. And let's go ahead and add a server as well over here. So in this end devices, we have a server over here. You'll see what this server does in just a minute. Okay, so we have a server over here. Let's go ahead and create the cabling. So our straight through cable. So now you know what that cable does. You click on this and fast Ethernet 0 and you connect it to the switch. So this user has connected themselves to the switch. No other configuration has been done by them. We also have a wire going from this PC1 over here. Let's say fast Ethernet 2. And let's go ahead and take a straight through cable and this time connect to the switch gigabit Ethernet 01 to our server, because server is going to be serving many different entities, so we give it a faster wire over a faster port. So fast Ethernet 0. So all of this is now connected. Just a side note, if you want to change the port of a particular cable, you can click on this little icon over here and then you can go ahead and move it around. Okay, so let's plug it back in. Okay, so now this is done. All right, so what do we want to do? First thing that we want to do is we want to ensure that this PC1 has the config set to static. Okay, we should have made sure that this was the case before connecting the wire, but it is there. Okay, so the wires are now connected. The PCs do not have an IP address. Let's go ahead and ensure that. Okay, so we go over here, we go to our desktop command prompt, and here we issue the command ipconfig. Okay, and as you can see, our IP version 4 address is 0000, which means it is not configured. Our link local IP address for v6 is this thing over here. And let's go ahead and figure out what the MAC addresses are. So over here in config, fast Ethernet 0, let's go ahead and take our MAC address and place it as a note over here. Okay, so let's go ahead and not delete it, place a note over here. So this is the MAC address of this guy. So it's over here. Let's go ahead and get the MAC address for fast Ethernet 0. Remember, each port has its own MAC address. So this is the port which is connected to our switch right over there. So our server config fast Ethernet 0 over here, we take this and we place a note over here as well, just to make sure that we can follow along with what things are happening. Okay, so this is the situation over here. Now what we want to do is we want to go ahead and first configure this server. So remember, what are we trying to do? We are trying to ensure that this network is already there, right? So let's say these one PC, this switch, and this server is already there. And what we want to do is allow any PC who comes in later on to join our network and not have to do any configuration, right? So all they will have to do is just set an automatic configuration switch, and then they should have all the configuration given to them by our server. So somebody has to give them that configuration. That is going to be this server over here. Okay, so this server is going to be our DHCP server. Okay, so let's call this the DHCP server over here. Okay, so this is our DHCP server, and what this server is going to do is it's going to hand out IP addresses to other people. But the issue is, if this server is going to hand out IP addresses to other people, it should at least know what its own IP address is. Okay, so what we're going to do is we're going to go to the server configuration. Over here in our fast Ethernet 0, we are going to configure this server, just this server. This is a one-time deal. The network administrator does it once. The users don't have to do it. So the network administrator comes over here, sets the interface fast Ethernet 0's IP address to static, and then gives it a static address. So 192.168.0.1. Okay. Typically, this is going to be a gateway, and the gateway typically has the one address, okay, just by convention, so that everybody knows that if somehow I need to go to the gateway, it's going to have one host. Okay, so click on this just to make sure that you get the subnet mask. Again, we're going to come back to what the subnet mask is later on, but for now, make sure that it looks like this for the server. Okay, so DHCP server has for its fast Ethernet 0 the IP address 192.168.0.1. Okay, so if you go to the desktop and command prompt, and here you say ipconfig, this server has an address. It doesn't have a gateway because it's supposed to be the gateway itself, but it has an IP address 192.168.0.1. This server is going to act as the gateway for all of this network that we have over here. Number two, it's also going to hand out IP addresses to everybody who connects to the server. Okay, so for that we are going to head over to our services over here. And here we are going to say that we don't need this HTTP, we don't need HTTP. Let's go ahead and close this. We do need DHCP, so it should be on. Okay, so service DHCP should be on. So we're going to click on this and it's going to be turned on. For DHCP, what we do is we create server pools or IP pools. What that means is we're going to have a collection of IP addresses, and when somebody comes in and asks us for an IP address, we are going to reach into the pool, find an IP address and give that IP address to them. Okay, so that is this thing over here. So here's the pool configuration. Start IP address. So your IP address pool is going to start from 192.168.0. Let's change this to 0. So the first person who comes to you is going to get the IP address 192.168.0.100. The second person that comes to you is going to get the IP address 192.168.0.101, and so on. Okay, so you have to specify how many maximum number of users you are willing to facilitate. So let's say at the moment we are just going to have like 25 different users. So what that means is my IP address pool that this DHCP server is configured for, that it is going to hand out, is going to have IP addresses starting from 192.168.0 to 100 all the way up to 192.168.0.124. So that is a total of 25 addresses, maximum number of users that we are going to hand out. Okay, so when a user comes in, the first time a user comes in, asks for an IP address, we are going to give them an address from this pool, which is going to be 192.168.0.100. Okay, so this is our pool from 100 to 124. But you don't just hand out the IP address to the people who come to you, you also tell them what their gateway address is, because again, you need the gateway address to communicate with devices outside your network. So it's an essential piece of information. So the DHCP server essentially does two things. Number one, it hands out the IP address to anybody who wants it. And when it hands out the IP address, which is going to be assigned to the PC, which has just joined, it also sends the default gateway address to that PC, and that we configure over here. So because this guy is our gateway and the DHCP server, both the same machine is the gateway, so we are going to say the gateway address is 192.168.0.1. Okay, so make sure that you understand this. This server over here, let's write this. So this is the MAC address and the IP address is 192.168.0.1. Okay, so this is our MAC address, this is our IP address. This is going to act as a DHCP server, and it's also going to act as a gateway. Okay, it's going to be connected to the internet or something over here. All right, So we are configuring the pool over here. We are saying whenever somebody comes and asks you for the IP address, give them two things. One, an IP address from this pool, and two, also tell them that this is the gateway that they should be using whenever they want to communicate to devices outside the network. Okay, so these are the two pieces of configuration we need to do. Now you go ahead and click on this save so that the server pool is updated over here. Okay, just to make sure that the configurations are right. So start IP address is 192.168.0.100, maximum users are 25. You forget about the TFTP and WLC, they're not important. DNS, again, we're going to come back to this later on, and the default gateway is 192.168.0.1. All right, okay. So now our network is set up. Let's say this PC guy just came in and they connected their wire over here. So as soon as they connect their wire over here, they are not going to have the IP address. So we can ensure of that by going to this thing over here and writing IP config. You can also go to config, desktop, and over here you can have IP configuration box over here. If you click on that, you can see this thing over here, but we don't want to use this because it's going to be different for different environments. So we try to stick with the command line and the config tab over here. All right. So here's what we're going to do. Do not do this. If you're doing this with the video, do not carry out the next step. First, what we need to do is don't click on this DHCP. Okay? Don't do it. We need to enter the simulation mode first because otherwise the packets are going to be lost. All right. So first we need to understand how the DHCP protocol works. And like I told you, we want to do this so that you understand what a protocol looks like on paper and what the semantics are for a protocol. So essentially a protocol, as we discussed earlier on in theory, is a set of rules. Okay. So what is the set of rules in the DHCP protocol? Here's a visual representation of this. Okay, so this is the DHCP protocol, just the very basics. So it has four basic steps. Okay, this is the basic scenario. There are other scenarios as well, but here are the 4 steps. When a PC comes in and tries to join the device, the network, when a PC comes in and wants to join the device, a DHCP server already has to exist on the network, which we just created. If a DHCP does not exist, then obviously the DHCP protocol cannot work. So the protocol is going to be a communication between two entities, the DHCP client and the DHCP server. The protocol is initiated by the DHCP client. What it does is it sends out a specific type of a packet, and the packet's name is DHCP discover. Okay, so that is the packet's type. Okay, you'll actually see this packet in just a minute. It has its own structure, but it's going to be a broadcast packet. And essentially what the client is saying is, can anybody give me an IP address? So it goes and announces to the whole network, the whole local area network. It announces to everybody. That is what broadcast means. It announces, can anybody give me an IP address? So everybody receives this packet. Everybody discards it except the DHCP server. When the DHCP server looks at this packet, it comes in, broadcast, the DHCP server looks at it, it says, aha, this has a request for DHCP for an IP, so I should respond to it. So what it does is, it sends out a new packet, which is called the DHCP offer. So this offer essentially means, yes, I can give you an IP address. Do you want to use this IP address? So it's going to send out a particular IP address, and it can be a unicast to the device which sent it, or it can be a broadcast. So it essentially broadcasts it to everybody, but you will see that the address of the requester is in the packet. Okay, we'll see this practically in just a minute. When this DHCP offer reaches the client, whether it's a broadcast or unicast, it uses the same switching protocol, the AR protocol, and it gets to you. When it gets to you, you look at this and you say, yes, I do want to use this IP. Are you sure I can use it? There are reasons for this different verifications, but these two are sent out necessarily. Okay, so you send what is called a DHCP request. So what's the difference between discover and request? In discover, you're asking for anybody to give you any IP address. In request, you have an IP address sent to you by some DHCP server, and you're saying, I want to use it. Can I use it? Right? And the reason for this is to ensure that no two different PCs have the same IP address. Okay, but that's not important at the moment. So when you send out this, are you sure I can use it? The DHCP server is going to respond with a DHCP ACK. ACK is short for acknowledge. So I'm saying, yes, you can. So yes, acknowledgement is yes. Okay. So this is what a protocol looks like on paper.
you define the steps which are taken by different entities involved in the protocol. So this is what a protocol looks like, and a protocol is supposed to achieve something, which in this case is that the DHCP client is going to receive an IP address, and it's going to also get the broadcaster, the gateway address, by the way. So it's also along with this, it's also going to be sent a gateway address. Okay, so let's see that in just a minute. Okay, so this is the protocol. We are going to look at all the packets which are going to involve discover, offer, request, and acknowledgement. Okay, so let's go ahead and close this. Let's make sure that we enter the simulation mode over here. Okay, so make sure that you are in the simulation mode over here, and then let's go ahead and bring out this PC0 over here. Okay, so I'm placing them side by side because it's essential for us at the moment. So what we are going to do is make sure we are in simulation mode, and we are going to click on this PC0's DHCP over here. Okay, so we are going to say that the gateway should be DHCP, or we can go to fast Ethernet and we can say the IP configuration should be DHCP. Okay, it's the same thing. So let's come over here in the global settings and click on DHCP. Okay, so as soon as I click this, you can see over here that a packet has been created, and this is a broadcast packet. Okay, so notice over here the default gateway is missing at the moment. That's because nobody has told us what the default gateway is. We have to figure it out using DHCP protocol. So the client has created this packet. Okay, so as you can see, we have the layer starting from layer 1. Layer 1 is the Ethernet. So the information is going to go out on fast Ethernet 0. So this is our physical wiring. We have already seen the physical layer, so you should know that this is the physical layer. In layer 2, what we are sending is from our address 8790, which is our MAC address, we are sending a broadcast packet out. So layer 2 defines that this thing is a broadcast. Okay, layer 2. In layer 3, what we are saying is the source IP address is 0000. Why? Why didn't we give this thing our own IP address? Because we don't have our IP address. But the important thing to notice over here is our destination IP is also 255.255.255.255, which, if you remember, is going to be all ones. So this is 8 bits of ones which turn into 255. Another 8 bits of ones, which is 255. Another 8 bits of ones, which is 255, and another 8 bits of ones, which is 255. So all ones is broadcast. Similar was over here. All ones was FFF in hexadecimal. All ones in decimal is 255, 255, 255, 255. It's the same idea. Broadcast address is all ones. Okay, so we are broadcasting on layer 2. We are also broadcasting on layer 3. Okay, so what this means is I don't have a particular IP address where I want to send this information. Remember, in our previous lab, we had an IP address 192.168.0.2 where we wanted to send the information. Now, I don't know what the destination IP address is. I don't know anything about my network. Okay, so in my layer 3, I'm going to put 000 as the source and broadcast as the IP, which means essentially anybody can accept it. Okay. In layer 4, we haven't done layer 4 at the moment, but just notice this thing over here. It says UDP. Okay, there are two options over here, TCP and UDP. At the moment, it says UDP. So you have to understand later on what this means, but for now, just forget about layer 4. There is nothing in layer 4, 5 and 6. And in layer 7, we have DHCP. So immediately looking at this, you can understand that DHCP is an application layer protocol. It's a layer 7 or application layer protocol. Okay, so what this means is it's going to put all of its information in layer 7 of the whole thing which is created. Okay, so if you click on this, we want to see some other details which are given to us by the packet tracer. So if you click on layer 7, it will show this to you that the DHCP client constructs a discover packet. Okay, so it's sending a so let's go ahead and all right, so the discover packet. Okay, so information, so it's sending out a discover packet. Remember, we have to have a discover, and then we have an offer, and then a request, and then an acknowledgement. Okay, right, so we have the discover packet over here. All right, so what it says, it constructs a discover packet and sends it out. Okay, so let's go ahead and close this. Now there is a little bit of a problem over here because when you send it out, it's going to take a little while. So you click on next and see that the broadcast packet has been sent out. This has been rejected by this guy over here, and it has been accepted by this thing over here. Okay, so let's click on this, and it says, so this thing over here, so it says that this packet has arrived over here. It's the same packet that we sent out. And in layer 7, it says the DHCP server constructs a DHCP offer packet and prepares to send it out. So it's going to send out an offer now. Okay, so the offer is going to have some information over here. Okay, for that, we have to click on this other packet, and it says over here that it's essentially sending out the information that yes, I have accepted the packet. Okay, so let's go ahead and click this. So this goes out and it reaches using a broadcast, it reaches the whole thing. So notice over here that here we have the last device and at device, and at the end we have the packet type over here. Okay, so let's reduce these sizes so that they are all visible over here. So what we are interested in is looking at only DHCP packets. Okay, so you can see the type of packets over here. So these are our packets. So this is just normal routing going on over here. Okay, so we're not interested in this. So if you click on this, now you're going to see quite a few different types of packets over here. So STP, click on next. There's going to be a lot of extra information going around in the network. It's not our concern over here, but you just have to understand at the moment that when a network is on, there is a lot of communication going on between different devices, stuff which we are not concerned with. Okay, so one of those is STP, another is ICMP. There is also going to be DTP and CDP. So there are these different protocols which are going on, which ensure that the network keeps operating properly. We are not concerned with those, so we are going to skip over those. Okay, so let's go ahead and click on this. So now see that a DHCP packet has gone out. So let's click on this and see that we have this gigabit Ethernet 0 over here, and this packet has gone out to the switch. And if you click on another next, then you can see that this packet has been sent out to both the PCs. So this packet, if you click on this, you will see that it has come from the DHCP server. The source address is 192.168.0.1. Okay, so see over here in layer 3, the source IP is 192.168.0.1 because it has come from this server over here. The destination IP is everybody, so it's a broadcast. Okay, so similarly in layer 2 over here, it has come from 74E4, so this guy over here. Okay, so let's move this out. So this guy over here, and the destination MAC address is also FFFF, so it's sending out a broadcast. It could have sent it out to this particular PC0 because it knows the MAC address, but it depends on the server implementation. Okay, so this packet which has reached over here, so if you click on this, it says this packet is a DHCP packet. The DHCP client processed it. Okay, so this packet has been sent out as an offer. So if you click on this, the DHCP client receives an offer packet. Okay, so this one, the DHCP client receives the packet, constructs and sends out a request packet. So it's going to send out a request packet in just a minute. But let's look at this one over here. So this was sent to us. This is a DHCP packet. The DHCP client does process it. It has to open it up and go all the way up to layer 7. And it sees that the DHCP packet is not destined to this host. How does it know? For this, it's going to drop the packet. But how does it know? For this, let's go to the PDU. Okay, so let's look at the PDU now. We looked at this earlier, but then skipped over it. Now we are going to look at it a little bit. Okay, so in this PDU, we have some preamble. This is some extra piece of information. We're going to come back to this. The destination address over here. So in the Ethernet layer, the destination address is a broadcast address and the source address is the server. Okay, so this is the server over here. All right, forget about the rest over here. We are only going to look at the relevant stuff. The source IP in the IP layer is 192.168.0.1 and the destination is a broadcast. Okay, again, because we don't know the IP address of the person that we want to send this information to. Then we have UDP over here. This is the transport layer. We're not concerned with this at the moment. Then we have DHCP. So this is the application layer information over here. So this is what the server has sent to the client. Okay, so what it's saying is your client address is 192.168.0.100. Remember, we said that it's going to go into the pool. The server is going to go into the pool, pick an IP address and send it to this guy. Okay, it's saying that the server address is 192.168.0.1. Okay, so this is what you should be using as your gateway. And you have the client address over here, which is 8790, which is this guy over here. And by looking at this PDU, this PC1 decided that this thing is not sent for me because the client hardware address over here does not match with its address over here. Okay, so that is why this guy rejected it and this guy accepted it. Okay, so let's go ahead and close this. And this guy has now accepted the PDU. Okay, so if you come over here, it has its own address, MAC address over here. So it's going to take this IP address and it's going to configure itself with it. Okay, so we are going to send out a request now over here. So a packet is going to go out. Okay, and this is going to reach this again, it's a broadcast packet. So it goes to this PC over here as well, but this PC is going to ignore it or discard it, and this server is going to accept it. So let's click on this and see this packet is a DHCP packet. The DHCP server processes it. the DHCP servers receives a DHCP request packet. Okay, and in the request packet, in the inbound PDU, if you go over here, it has the same information. So essentially what it's saying is, can I have this IP address? And now the server is going to send out the DHCP server binds the request IP address from the pool to the host MAC address. So in its own configuration, this server is going to record this information that the Ethernet address 0005 5EE8 8790 has been assigned the IP address of 192.168.0.100. Okay, so this address over here has been bound to or given to or assigned to this guy over here, and then the server is going to send out an acknowledgement. Okay, so here goes the acknowledgement, and this acknowledgement is going to get to again both PCs, but this thing is going to ignore it and this is going to accept it. Okay, so the DHCP client receives a DHCP acknowledgement packet. The DHCP client receives an ACK packet and sends its IP configuration. So see over here, as soon as the packet has arrived over here, the gateway has appeared over here, and if you go to this thing over here, we have a 192.168.0.100 IP address assigned to us. Okay, so this is how this whole thing works. This server in its DHCP, it had this whole configuration, and when this guy came in and asked for the IP address, now it has been given the IP address. So all we had to do, remember, let's exit the real time over here and do this same thing for PC1. So all you have to do is connect the wire, go over here and click on DHCP, and that's it. It's going to take a little while, but you are going to be given the gateway and you are going to be given the IP address 192.168.0.101. So the PC people, when users come in and try to connect to your device, your network, all they have to do is just click on the DHCP. And nowadays that DHCP click is also the default option. So all you have to do is connect the wire and you're good to go. Okay, so this is the end of this protocol. Remember, why did we do this protocol? Number one, we want to take a look at the IPs in further detail now. We want to look at how the communication is going on over our network. We also wanted to make sure that we look at a protocol, because later on we are going to say that a protocol looks like this and a protocol looks like this. So you have to understand what a protocol looks like. So it's essentially a set of rules. Here the rule says first you send out a discover, and then you send out this, and then you send out this, and then you send out this. Okay, so these are the rules which are followed by all the devices, and the devices know that this is how we're supposed to do this. The DHCP protocol packet that you saw over here, the exact information in the PDU, we are going to look at this in the theory. What exact bits, how many bits, for what thing, that is all going to be in the theory when we get to it.